I think we now have the tools necessary to actually go ahead and solve the Solow model. First, let me remind you of a couple of things which we showed or assumed in previous lectures. Number one, S is equal to I. This is true by simple national income accounting identities, right? Secondly, consumption in the economy is given by this, which implies savings is given by this. This is a behavioral assumption on consumers, which is of course a very Keynesian assumption. The consumption function here looks just like the Keynesian function, except the autonomous part is stripped out. Lastly, labor force evolves in this manner, which implies that L dot L is equal to N. The way this assumption is made is that labor force participation in the economy, the rate is constant. The population grows at this constant rate of N, small n. Also given by eta, the Greek letter eta in certain textbooks, but we just take it to be N. It's much simpler to pronounce and to write. So with this setup, let's go ahead and solve the Solow model. Understand the I here stands for gross investment, which is the increase in capital stock of the economy. This is gross investment. But when you want to know the change in capital stock, you need net investment, right? So net investment is gross investment minus depreciation. Again, basic national income accounts. So the net investment, which is equal to the change in capital stock of the economy, is equal to S minus depreciation of K, right? Now S, I already told you, is S of Y, and this is again something we have seen in previous lectures, an assumption that a constant fraction of capital is depreciated every year, or whatever, every period. Since we are dealing with continuous time dynamics, you have delta K, right? So this is the law of motion of capital. All right? Okay. Now, you know that small k equals capital K by L, which implies, and this should be second nature to you by now, that this is true. This is Sy by K minus delta by minus N. Now I can divide capital Y by L and capital K by L and get S of small y by small k minus N plus delta. Now if you multiply by both sides by small k, you get small k dot equals Sy minus N plus delta small k. A natural question should then be, why are we doing any of this at all? The reason is that this system cannot be solved, in the sense that it doesn't have a steady state, and you're going to see this later. But the point is, capital K never really comes to rest, so to speak. So you had, just give me a sec, yeah. You have small k dot equals Sy, and so we derived this, and this can be written as S f of small k minus N plus delta small k. This is the motion, so to speak, of small k. What is a solution to this? A solution to this is when small k comes to rest. That is, small k doesn't change anymore. So solution to this is this, right? This is the equation which characterizes, or this is the analog to the equilibrium conditions we usually talk about. So If you solve this equation, you'll get a solution of this form. And you solve this for KSS to get small k at steady state. This is largely standard, I think. Diagrammatically then, let's just look at the standard production function. So this is f of k. S into f of k therefore looks like this. You know n plus delta looks like a straight line. And so where these two are equal, you have KSS. Right? This is what steady state looks like. Now we are going to deal with two things about this steady state. And this is where we need to be a little careful. Two questions. When does KSS exist? When is it stable? These are two questions then that we want to answer. Okay, so the first question, when does it exist? Right? The answer to that is concave production functions with Inada conditions implies it exists, but it may exist in other cases as well. Okay, let's first deal with the other cases and then we'll deal with the concave case. So when you have a convex production function, you may or may not have a steady state. Suppose you had this or you have this, right? So here there is a steady state, here there is no steady state. So it may exist, it may not exist. Even when it exists, it's not stable, something we'll deal with when we talk about question 2. Similarly, under linear production functions, you might have SFK is this is n plus delta k. You might even have this as a SF of k or this as SF of k, the same line as this. Again, in all cases, no steady state, and you have infinitely many steady states. Trivially true, because the two lines are always alike. Alright, so now on to the case of concave production functions. Many people think that concavity guarantees existence. This is not true. So let me give you two examples to show that. Right. So this is a concave production function and its transformation, no steady state, right? Similarly, no steady state. Again, both these production functions are concave. Slope is very clearly decreasing, but you don't have a steady state in either case. Why? Inada conditions are not satisfied. So Inada not satisfied. Here, if try to answer this yourself before you watch the video, which Inada condition do you think is not satisfied here? The answer to that is, as small k tends to infinity, f dash k is not going to 0. In fact, it is positive. Right? So you can see asymptotically you're going down this positive slope. Here, limit as k tends to 0 plus of f dash k is finite. It's not tending to infinity, as you can see, right? Right at the beginning, you should have a vertical tangent essentially, but you don't really have that. But when inada conditions are satisfied, you will necessarily have a steady state existing if you have a concave production function. That is trivially true because there you go. This is what SF of k looks like. By the way, again, the reason for this is that the derivative of this is SF dash k, so the limits applied to f dash k 0 and infinity, even when multiplied by s, do not change. So why does a steady state have to exist? Because initially your SF of k must exceed the depreciation line, and eventually it must go below the depreciation line, because the depreciation line always has positive slope, while this is eventually going to 0, which means a steady state must indeed exist. So just to go back then, these are the two questions. This was the first question and this was the answer to this. If it's concave and the inada conditions are satisfied, there has to be a steady state, which is why we assume those things in the standard Solowian system. But it might exist in other cases as well, in the sense that you have KSS to solve the equation SFK equals n plus delta k. So this is existence of the solution to the Solow model in terms of a steady state where small k comes to rest. But there was this other question: when is it stable? To answer that, we must first ask what stability even means. So here we are largely talking about stability. Stability means global stability, which means that you have a KSS when it exists, sure, but when k is away from that, maybe more than that or less than that, does the system by itself lead you back to the steady state value of k? That is what global stability means, very loosely speaking. So the answer to this is, again, it depends, but convex production functions give you globally unstable steady states insofar as they exist. But again, if you have a concave plus inada production function, you're going to get a steady state which exists, but b one that is stable as well. Let's first deal with instability then. Or okay, first let's deal with the very standard case to understand what stability even means. So this is SFK, this is n plus delta k. What does stability mean? So sure, a steady state KSS exists. Suppose you're off this then, right? Suppose you're here. Suppose you're at K1. Do you go back to KSS? The answer is yes. The reason is that now that you're at K1, which is lower than KSS, but your SF of K is greater than n plus delta K, right? Which means net investment, loosely speaking, in terms of capital per worker is positive. So you increase small k and you go here. Then the same process is repeated while you reach this point. I don't want to get too in depth into this because you probably know this already. Similarly, if capital per worker is too high, at this point net investment is negative and you go back and reach here. So this is globally stable. Convex production functions do not give you globally stable steady states, right? So insofar as they exist, if they don't exist, there's no question of stability anyway. All right, so you have this. Let's say you're here. So a steady state still exists. KSS definitely exists. But at this point, your capital is too low. Capital per worker is too low. But net investment is negative because depreciation exceeds SF of K, gross investment. Which means capital stock will further reduce and you're going to go back to 0. Similarly, if you're here, your capital per worker is too high relative to the steady state, but your net investment is positive here. So you're going to go on increasing and increasing till small k approaches infinity. So this is not globally stable. So now we've looked at a few things. First, what is the law of motion of capital? We then derived the motion for small k from that. Then we saw what a solution to that system looks like, when it exists and when it is globally stable. To end this video, I'll just solve a very trivial case, which is obviously the Cobb-Douglas case, to see whether steady states exist there and what the steady state is, algebraically speaking. So you have f of k equals k alpha. You know small k dot is equal to sfk minus n plus delta k. So this is sk alpha minus n plus delta k, right? If you set k dot equals to 0, then you get skss alpha minus n plus delta k ss equals 0. And after some basic algebra, what you're going to get is this. This is the steady state for the Cobb-Douglas production function. It exists because the Cobb-Douglas production function satisfies the Inada conditions and is concave, and it's stable because of the same reason. Understand why? It's very obvious, really. F dash k equals alpha k alpha minus 1. F double dash k equals alpha into alpha minus 1 k alpha minus 2. Remember, alpha is between 0 and 1. Why? Ask yourself why. The answer is going to be fairly obvious. The reason, of course, is that it is a CRS production function, so alpha cannot be greater than 1. Okay, what does that then mean? Concavity is trivial because this is obviously positive, but this is negative, right? Because alpha is between 0 and 1, so when you subtract 1, you're going to get a negative value. This is positive, so f dash dash k is negative. On Inada then, you have f dash k equals alpha k alpha minus 1. So this can be written as alpha by k into 1 minus alpha, and this 1 minus alpha is positive. So when k tends to infinity, f dash k is 0, right? Because this denominator is tending towards infinity, and since this is a positive power, that is true. And when k tends to 0 plus, this whole thing tends to infinity, or it's equal to infinity. Again, because this is a positive power, so you're essentially, you have an alpha by 0 form, which is obviously an infinite limit. So for the Cobb-Douglas production function, steady state exists. Steady state is equal to this, and it is also stable.